Hello everyone. Before I explain how to draw Bode plots, I thought it would be a good idea to again quickly go over some of the theory behind Bode plots so that you are comfortable in interpreting what Bode plots represent. Because it's quite important, if not more important than drawing them, for you to be able to interpret them. I also do want to point out that there is quite a lot more to Bode plots than what I will explain here, but what I will discuss here will only be relevant for the time being, or at least for the module. Okay. Thus far, we have considered inputs working or operating at a specific frequency. And we defined this input which looks like u of t is equal to b times sine of omega naught t plus phi. Okay, b is your amplitude of your input, omega naught is your operating frequency, and phi is the phase of the input. We showed that if this input is applied to some system, let's say the system is defined by some transfer function t of s, then the output will look like this, or at least the steady state output is equal to b times the magnitude of your frequency response transfer function at the operating frequency omega naught times sine of omega naught t plus phi plus the phase angle of the frequency response transfer function at omega naught. Okay. Just before I continue, I noticed that I made an error in the slides, lecture 20, where I said that is a cos term, and it shouldn't be. It should be a sine term. If your input is a sine term, your output should be a sine term as well. Okay. We said that this output equation can be interpreted like this, that this number is an amplification or attenuation factor, and that this number is the amount by which your output leads or lags your input. Okay. We also did an example where I used tutorial 7's test question to illustrate this, and the tutorial 7's test question gave a transfer function that looked like this. It was 1 over s plus 1 with an input to the system given as 2 sine of pi t. So the operating frequency was pi. And of course I asked you to determine the output. So if you did this correctly, well, unlike me, I saw I made a mistake in the slides again. If you did it correctly, you should have determined that the output was this, where it's 2 times this amplification factor, which was 1 plus pi squared, all over square root times sine of pi t minus the arctangent of pi. Okay, so we see that the output of our system is attenuated. I use the word attenuated because that factor is smaller than 1. If you go work that out, it should be around 0.3. And we see that the output lags our input by the arctangent of pi. If you go work that out, that should be about 1.26 radians, or 72.2 degrees. Okay. We can confirm this if we do the time domain plots of the input and output on the same axis, or same plot, and I've done that. We can go to MATLAB and we can do those plots. And we can quickly borrow this figure. Okay. What's the easiest? Let's look at the amplification factor. Okay. Let's zoom in here. This value, which is the amplitude of our input, is obviously 2, as can be clearly seen. And that data point is approximately, I would say, 0.6. So we can say that, alright, we know that this frequency is at pi radians per second. So our amplification factor should be then output over the input, so that should be about 0.3, and that is exactly what we got when we did the maths. Okay. Working out or looking at the phase difference between these two graphs is a little bit trickier, the reason being that this is on time scale, so we just have to convert that to radians. So we just have to see what the difference is between this, and that is in this case time. And I think the easiest would be to go and fetch that from MATLAB. So that is about 0.518 and 0.9. So the time difference is about 0.41 seconds. And we can work out the phase difference in radians using this equation, omega t. So that should be the omega is our operating frequency and the time difference is 0.41. Okay, if we work that out, we should get about 1.26 radians, and that's exactly what we worked out with the maths. Okay. Okay, so this was, of course, at a specific frequency of pi, and if we want to determine this amplification factor and the phase lead or lag at some other frequency than pi, then of course we will have to recalculate this magnitude of our frequency response transfer function at that specific frequency, and of course the same with this phase angle. And we will have to recalculate those factors or numbers for every frequency of interest. And this is exactly where the Bode plot becomes useful. Instead of calculating this magnitude of the frequency response transfer function at, and the angle at every frequency of interest, we determine these numbers or as a function of omega or frequency. So we, instead of determining j omega naught, we just determine it as a function of frequency. And we plot this magnitude and angle as a function of frequency. And this is the Bode plots. And once we've did those plots, we can just read off the amplification or attenuation or gain and phase shift of our output at the frequency of interest. Okay. I think it's best we go over the example again to explain this. And let's consider first, again, our example that we did earlier, where our transfer function was 1 over s plus 1. And we can easily draw the Bode plot of this system in MATLAB. And I've done that as well. Okay, and let's borrow this plot for a second again. Okay, and let's use this Bode plot to just confirm whether our amplification or attenuation and phase angle at the frequency pi was correct. Okay. First, let's find the frequency pi on this frequency axis. So that's 1. That's 2, that's 3. So I would guess that 3.1 should be around there. So let's try and draw a straight line. It's definitely not a straight line. And try and read off the phase at the frequency pi. Okay, that's also not a straight line. A little bit better, alright, but anyway. We know that this half distance between minus 45 and minus 90 should be minus 67.5. So it's reasonable to assume that this phase angle is that phase angle that we calculated, which was 72. What was that? 72.2 degrees. Okay, let's look at the amplification factor. Let's try and draw a straight. Some bar there. Alright, I would say that this value is about minus 11 decibels. Okay. If we want to find the amplification factor, we don't want it in decibels, so we're going to have to do the conversion. Alright, so if we work that out. Well, I'm not going to work that out, but that should be what was the magnitude was 1.3. You should get about 0.3 if you work that out. Okay. Okay. As I've said in class, there's some other useful things we can read off from this Bode plot. We can see that for low frequencies, let's say lower than 1 radians per second, we can see that the amplification factor is a constant, and that's 0 decibel, which translates into 1 for our amplification factor. So approximately for this range of frequency, less than 1 radians per second, the amplification is 1, which means our output is the same amplitude as our input, and this means what we usually term it is that the output follows our input very well, or sometimes in control systems as well we use the term it tracks our input quite well, yeah. So what we call this frequency range where the output tracks the input quite well, we call this the bandwidth. Alright, and this maximum frequency at which the output tracks the input quite well is called the break frequency. Let's give it a subscript B, omega B. Alright, so after this break frequency, the output, or the output starts falling because the amplification factor gets smaller than 1. So your output starts falling. Okay, so here at low frequencies, our output tracks our input quite well. It doesn't go higher than the input, but it tracks our input quite well. But then the output starts falling. And this is the reason why we call this a low pass filter. Because it doesn't, the outputs, it doesn't allow high frequency, at high frequencies, it doesn't allow the output to go through. That's why we call it a low pass filter. Okay, I'm sure you can interpret the phase on your own. It's quite easy. Okay. The last thing I think I want to mention about the sort of giving introduction to Bode plots is just to talk about the axis of the Bode plots. Just to point out, because I want to clear up some confusion I may have caused in class. Okay, so of course we know that the Bode plot consists of two plots, the magnitude and phase plot, and this magnitude plot, the scale is a decibel scale. So that means it's a 20 log of the magnitude of your frequency response transfer function. Okay, and this is the angle. Alright, but this is where I want to clear up the confusion. It's that the frequency axis on both of the magnitude and phase, we plot the actual values of omega just on a logarithmic scale. Okay. I think I may have confused you by giving you an impression that we plot the log of omega values on this frequency axis. Okay, so just to avoid confusion, I think I will I won't write log omega, I will just write for the frequency axis, I will write omega, and I'll give the units radians per second. But just remember that omega is plotted on a logarithmic axis. Okay. Lastly, before we start diving into drawing Bode plots, recall that I said in class that all transfer functions are made up of 4 building blocks, and they can be decomposed into these 4 building blocks. And we can, when drawing these, we can merely add or subtract the Bode plots of each of the building blocks. And the reason why we can do this is because we are working or plotting in a log domain, which converts multiplication to addition and division to subtraction. Okay, recall that I think I'm going to review these building blocks quickly. The 4 building blocks were let's call this a positive or negative constant. Alright, so let's call this, for the positive, let's call that T1 of S, and then for the negative, call it T2 of S. Second building block was poles and zeros at the origin. Okay, so let's call the pole T3 of S is equal to 1 over S, that's a pole at the origin, and then T4 of S is equal to S. That's a 0 at the origin. Alright, third building block was real poles and zeros, not at the origin. And let's call the pole T5 of S, and we write it in this form, and the 0 we write it in this form. You know what, I'm going to use, to avoid confusion with the omega naught we used earlier, I'm going to use B, because this, as it turns out, as I'll explain later, this omega which we use here is called your break frequency. Okay, the fourth and last building block was complex poles and zeros. So let's use T7 of S for the pole. Again, let's use the B. Plus 1. It's going to be a little, so let's use T8 of S for 0. And again, I see I've made a mistake, or someone pointed out in class that I've made a mistake in the slides in defining this transfer function for the pole. So just have a look. I think I didn't use brackets. I just said this, and it should be this. Alright, so these are the building blocks, and we will look at how to draw each of these building blocks and how you can combine them to draw more complex transfer functions in the next few videos.